Thank you very much, and good morning. 9 a.m. is a brutal time, but we managed to all be in this room. As Carl Henrik mentioned, I'm now a lecturer at the Department of Epidemiology and Biostatistics, and I wouldn't be mentioning it if it wasn't relevant. So the thing is, it is relevant. We are here today together for 1.5 hours, if I'm correct, right? And the whole session will be broken up into 3 parts. The first part we will spend on motivation. And the thing is, there's probably, like with any topics, as many views on Gaussian processes as there's people using them, right? So you spend the whole first day listening to 2 introductions. And what I'd like to say, you can treat this talk as introduction 3. So in the first part, I will just try to explain the angle at which I come to Gaussian processes, as do many colleagues of mine as well. So the second part, you can literally think as introduction 3. We will recap a little bit what you did yesterday, and then we will add a little bit more material on top. And then the meat is actually in the third part, in the practical aspects. So knowing all this theory and having developed these intuitions, what do we do with it? So let's start with spatial statistics. And to wake up, I'd like to ask you a question. What do you think Jon Snow and Gaussian processes have in common? They know nothing, okay. More answers, more answers. I wanted to say wrong answers only, but no, try to give correct answers too. Sorry? Spatial inference. Okay, I kind of hinted at it, right? Bad of me. So usually, okay, one new person. Okay, you're a little bit late. You have to answer a question. What does Jon Snow and Gaussian processes have in common? Just 9 a.m. 9 a.m. brains, I know. So usually a room splits into 2 parts. Some people say they know nothing, the winter is coming, which wouldn't be unreasonable now because we're at summer school, it somehow feels like winter. But actually, there is a difference in spelling. Jon Snow, the winter is coming, is spelled without H. Jon Snow with H is the father of spatial epidemiology. So what Jon Snow and Gaussian processes know how to do, they know how to make disease maps. Turns out Gaussian processes in epidemiology are used in very versatile ways, from nowcasting, then making surrogates for downstream decision making, and also to make disease maps. And disease maps is in bold because this is what I do, my colleagues do, the favorite topic. So disease mapping in public health actually have been a very, very old tool. It might come as a surprise to you, but the oldest map of a disease we have dates as 1691, when Italians made a map of containment areas. Then closer to modern day, and also geographically closer, were the maps of 1854, when Jon Snow, who we already mentioned, actually mapped the cases of cholera in London. And the theory back in the day was that cholera was spread by miasma, bad air, and Jon Snow performed this investigation where he mapped out how water was distributed in London. Turned out there were only 2 water providers. And then he realized, okay, here are all the cases, and I can track all of them back to this water pump on Broad Street. So I'm very ashamed. I've been in the UK for 5 years now. I'm an epidemiologist. I still haven't been to the Broad Street. But if you're ever there, go say hi to the pump. It turns out, the Twitter account of Jon Snow Society tells us it's exactly 170 years and 2 days till today that Jon Snow made the claim that the handle of the water pump should be removed. This map I'm just particularly proud of because it is also a map of cholera, same days as London. Look at this map, super simplistic, right? This one is so detailed, very precise. Why? London, Oxford, this is a map of Oxford, of course. And I live in Oxford, okay? This map is stored in Bodleian Library in London, also one of the most detailed maps of a disease back in the day. If you are interested in cartography of disease mapping, there are wonderful books by Tom Koch. And fortunately or unfortunately, we're here not to talk about history, not disease history, but about Gaussian processes. So what do we want to do? We want to be Jon Snows of today, modern Jon Snows. And the tools we have today are different. Of course, we have data, which is very similar to the data that Jon Snow had. However, our data today is way more precise. It is geotagged. It is of spatio-temporal nature. And also we have different methods at hand. Bayesian inference, of course, spatial statistics, and main tool of spatial statistics and disease mapping is Gaussian processes. Couple of more items to mention. So now I'm just explaining the building blocks of the whole talk. You will have another whole session on non-Gaussian likelihoods with T today. That's why we're not going into much detail, but what we need to say is that this whole inference framework in which we are placing ourselves, first of all, we're going to use hierarchical Bayesian models, which include latent Gaussian processes. This is a typical structure of the model. Not 100% of the models look like this, but really many of them, maybe perhaps 90% of models in spatial epidemiology. So what is what here? Of course, there's some outcome data. Why? I guess we don't have a pointer, do we? This is something that looks like a pointer, but I don't think it's a pointer. It's okay. So the top line is the data. Starts imagining some space. For example, the UK. The UK is subdivided into small areas. For each area, you have a certain outcome, Y. Then we choose an observational model. Usually, it is dictated by the type of data. Are we modeling proportions? Are we modeling counts? And what is important, the likelihood, pretty much never in practice in the space of epidemiology, is Gaussian. Then at the linear level, there are usually two terms, the so-called fixed effect and spatial random effect. The fixed effect today we're not going to talk about. You can think of axes as covariates. So if we're in a situation of studying an environmentally driven disease, such as malaria, which is transmitted by mosquitoes. Mosquitoes only like some areas, don't like some certain areas. That's why X usually would include such information as altitude, vegetation, proximity to water, urban environment, and so on. What is important here is this term F, which of course is the Gaussian process, which reflects the correlations in space. And Gaussian process is described by its own set of hyperparameters. I guess you spent a lot of time yesterday looking at this type of things. So only a couple of points to make here about non-Gaussian likelihoods. If likelihood is Gaussian, we live in a wonderful world. However, us epidemiologists never do. We live in the world of doom where all likelihoods are non-Gaussian. And having model structure as neat as I showed on the previous slide is also quite a luxury. But for today, let's assume that's where we are. So here's a list of some common likelihoods, such as Bernoulli distribution if we model probabilities from something from 0 to 1. Or usually we often use binomial, negative binomial for counts, and so on. So T will tell you a whole lot about that. So now let's cover the types of spatial data. And it again might come as a surprise. There's only 3 types. I don't know if you find this news unsettling. I definitely do. So during this lecture, try and challenge yourself, and me as well, and the authors of the book, and the whole spatial statistics field. Maybe by the end of this hour, you will be able to come up with a 4th type of spatial data. Then definitely let us all know. But here are the 3 types that usually we target with our models. So the first type of spatial data, so-called aerial data. I already mentioned this piecewise constant structure. Now we're looking at the map of United States, which has administrative subdivision into areas. And the tasks that's associated with this type of data is called small area estimation. Why? Because in some large areas, we usually will have more data, and raw estimates there would be more stable, robust. There are, however, many small areas where we might not get any data at all, or we might get very little data, so estimates are not robust. The idea here is to borrow strength from neighbors. So we try to smoothen our data, but the spatial structure is given. It's not something we as modelers choose. It is predefined. So we're now in the UK, right? We have shires, or how are they called correctly? I always forget. Also, in the UK, we can work with so-called LTLAs, low-tier local authority areas. They're really tiny. There is about 400 of them, but they are predefined. And why is it important to know how to work with this type of data? Because this is the spatial subdivision at which decisions are made. Second type of data is geostatistical. I guess you would have heard yesterday of kriging, of the task of kriging. What does it mean? It means we have observations in some locations in space, and we want to predict what's happening in unobserved locations. The third type of spatial data is so-called point pattern. Locations here are not selected by us. Let's make an example for geostatistical data. This could be meteorological stations. They're fixed somewhere in space, right? We can't move them around. And in this point pattern data type, the locations are not fixed. They are themselves the data. Where did the cases take place? Where did the event occur? So, and the task then, from observed locations of events, we would like to reconstruct the whole intensity surface. And vaguely, models of aerial data use some expression that is, of course, reminiscent of Gaussian processes. This is a multivariate normal distribution. Then how this covariance or precision matrix Q is structured is a separate story. What we would like to pay attention to now is that all these models are based on 2 quantities. There are 2 matrices, D and A. So A is the adjacency matrix telling us who is neighbor with who, and D is diagonal matrix telling us how many neighbors does each area have. The kriging then goes more into the space of classical Gaussian processes. So do point pattern models. So log Gaussian Cox process perhaps is the most straightforward, commonly used model for point patterns. And even though the likelihood looks more involved than for the models we saw so far, as said, at the linear level, everything still boils down to the exact same term, x beta plus f, where f is the Gaussian process. So when we would like to model point level data, geostatistical data, point pattern data, here we as modelers do choose the computational grid. So here it's completely up to us. What is the resolution and where are the points where we would like to make predictions and how many of them. So what about networks, right? I started this section saying there's 3 types of spatial data, period. What about networks? So I'll pause there. We don't need to answer this question right now. But let's keep it in mind. So stay tuned. You'll have to listen to the very end of the talk and pay attention to find out. What do we do then? Networks and graphs. Okay, the second point we need to make is about inference methods. Again, I believe you already would have heard about some of them, and in this setting, we would like to be using Markov chain Monte Carlo, among others. Why? And what do we need to know? So first of all, the Monte Carlo method itself, we're not going into details, but there is one fact about it that we will use today, and that is it's a magical method which uses random numbers or random number generators to estimate deterministic quantities. That's incredible, right? Using random quantities to estimate deterministic quantities. In particular, we know how to estimate, how to approximate an integral of function f with respect to density p. If we just draw points from density proportional to density p, and then we can just average values of function f at those locations. So that's first item we need to carry on into the rest of the talk. And second thing to know is that Markov chain Monte Carlo is a set of very elaborate but iterative algorithms, and they have convergence guarantees. So they're absolutely wonderful, but they're iterative and they take a long time. How do we use MCMCs? We don't usually write them by hand from scratch. There is a whole set of tools out there called probabilistic programming languages. I've listed just a couple of them here, but why are they so good? They allow us to focus on the modeling, so we think about the model, how to formulate the model in most efficient and expressive manner. Then we know that MCMC has theoretical guarantees, and probabilistic programming languages also provide us, along with implemented MCMCs, they provide us with diagnostic tools. So when they spit out a result, we can look at some diagnostics and be able to tell, can we use those results or not? So as modelers then, what do we need to know to be able to do? 3 things. Well, 2.5 things. First, we need to know how to specify priors, or let's generalize it, the generative mechanism. We need to choose a likelihood, usually is dictated by the data type. And sometimes with some PPLs, we need to choose the inference algorithm. And this is it. Then we press the inference button and wait to get the samples. Let's take a look at an example. So here's a very simple model. Data y comes from normal distribution. We place some priors on parameters mu and sigma. How does it look in a probabilistic programming language? So this is an example in NumPy. It's literally what we write with pen and paper when we write the maths down, prior for parameters, and this line corresponds to likelihood. So the only difference between the line specifying prior and the likelihood is this tiny expression at the end. We say ops equals data. So the line where we point at data is the likelihood. And yes? Data play. You can think about it as a for loop. It's just a very efficient for loop. And this is it. So the first 9 lines now on the slide, this is the whole program. The rest allows us to, this is us creating some fake data. Then we choose the inference mechanism, nuts in this case. Then we call MCMC sampler and get the samples out. We didn't need to know anything about MCMCs, how they work. It's useful to know how they work, of course, but we didn't need to implement any MCMC from scratch. So, okay, we're at a Gaussian process summer school. How would it look like for GPs? We do choose a kernel function, and then all we need to call is the multivariate normal distribution with covariance matrix. Okay, if you would like to play with this or other examples, there is a link to the more lengthy sequence of programs online. Slides will be available, so you'll have this link. Right, once we have the samples, what can we do? Let's now see if you have experience with MCMCs. Let's say we pressed that inference button, got the samples out, now looking at this plot. This is a trace plot, right? Shows me how the samples looked like. Can we use them? Can we not? Is it a good trace plot? Is it a bad trace plot? Who thinks it's a good trace plot? Sorry? We're not showing you where's the burn-in, right? We'll just say, here's 1,000. Here's 1,000 samples. Can we use all of the samples? Sorry? Theta is some parameter of the model. So we had a model, ran MCMC, and theta is our parameter. Who thinks it's a bad trace plot? More people think it's a bad trace plot. Yeah, this is a terrible trace plot. Why? So what we want to see is stationary trajectories where all 4 chains agreed with each other, each chain agreed with itself. Here's a much better trace plot. And here we actually do show, here's the burn-in, the gray area. Okay. This is the magic of probabilistic programming languages. It just allows us to make those plots, to look at the numbers, what are other good diagnostics of convergence. Gelman-Rubin statistic, effective sample size usually is informative too. But here at the Gaussian Process Summer School, all we want to think about, and as modelers also all we want to think about, is how to sample from the GP pri within such a program. And here we come to the second part. Remember, the second part is equivalent to your introduction 3 to Gaussian processes. We will recap now some material that I'm sure you heard yesterday. So maybe some of you can tell me, participants, how would you sample from the Gaussian process? So imagine you are writing that program in a probabilistic programming language, and all you need to do is to say, here's F. I want to generate priors for F, where F of a Gaussian process. So what are your options? How would you do that? Based on yesterday, what you heard yesterday. Yes, please.
You just have a finite-dimensional multivariate normal, and that's your...
Great. Finite-dimensional multivariate normal. You sample from it. How do you sample from it? So, Right. Okay. So the answer you're giving, I guess, is linked to the kernel view. So what we're going to discuss now are different views at Gaussian processes. So the kernel view is a generalization of this multivariate normal. This is, I guess, most of you would have thought of this multivariate normal. Let's draw samples from there. So we start with a finite-dimensional multivariate distribution. How do we describe it? With mean vector mu covariance matrix K. And then if we start viewing the elements of those vectors as evaluations of some function f at a finite number of points x, and then if all of those f of x are jointly distributed in a Gaussian manner, then they form a Gaussian process. So this is the formal definition, I guess, which you saw yesterday, at least twice. So Gaussian process is defined potentially infinite index set. And it means that if we take a finite set from the index set, evaluate f on it, then the result is distributed as a multivariate normal. So here, analogously to the finite dimensional case, we need the mean function and covariance function. So now instead of mu, we define mean, denote mean as mu. Covariance function is k of x prime. Why is this a useful way of representing Gaussian processes? Because it allows us to encode prior knowledge about functions, right? And what does that function of two parameters k do, k of x prime? It tells us about similarity of the outputs of the function at inputs x prime. So in this way, also, GPs give us, we can think of them as priors over functions. This is an incredibly useful and practical way to think about them. So let's discuss k for a little bit. Can any function of two parameters be a kernel? Probably not, right? It has to be positive semi-definite. So I will be a little bit sloppy throughout the talk, but most cases when I'm sloppy, I'll tell you that I'm sloppy. So we want it to be, let's say, positive definite. If it's semi-definite, well, when things collapse to zero, usually it means something would collapse to some particular regime. It's still, the process still exists. But I will interchangeably say positive definite, positive semi-definite. So what does it mean for a function of two, for kernel here to be positive semi-definite? Well, what is a positive definite matrix? A. If we take any vector v and form the scalar product of v and av, which we can write in Rn as b transposed av. So this expression has to be positive for any vector v. Then matrix A is positive definite. And this definition translates to kernel. So if we evaluate function k, function of two parameters, at any set of x's, this gives us a matrix, right? And if we plug the values of that matrix in the expression we just saw above, then it also has to be greater than 0 to be positive definite, or greater or equal to 0 to be positive semi-definite. This is the matrix I just mentioned. We collect all the evaluations of function k on our inputs x. So again, what does this matrix tell us about? Apart from being a gram matrix, it tells us about similarity. So how similar are the values at these two locations? Notation for today, perhaps similar to what we used yesterday. Again, we say f is distributed now as a GP with min m and covariance k. For the rest of the talk, we will set m to be equal to 0, and we'll be talking mostly about k and how to deal with it. So to recap, what does it mean f is a GP? As we were already told, f is a GP with kernel k, means that if we take a finite set of x's, evaluate f at this finite set of x's, we get a multivariate normal distribution now with matrix k. Matrices is now something we can work with. So second point of being sloppy, I do not make vectors and matrices bold. Mostly it will be clear from the context who is a vector, who is a matrix. Okay, so now kernel view gives us understanding of Gaussian processes as priors over functions. And this is also a moment representation, right? So we said that we can define a Gaussian processes by saying what is the mean function and what is the covariance function, which are the first and the second moments. Then by choosing a kernel explicitly, we choose what are the properties of functions that we would like to encode. What are properties? Continuity, differentiability, periodicity, symmetry, stationarity, non-stationarity, whatever behavior we would like to encode. This is what we explicitly can use the kernels for. Let's take a look at a couple of examples. I am sure you would have seen this kernel yesterday at least 2 times. Squared exponential. I used to call it RBF, but then one day T told me, why do I call this kernel RBF? So it's for T, especially throughout this presentation, I have renamed everything to squared exponential, SE kernel. You would have heard probably other names for it. Today, let's stick to SE, squared exponential. So looking at the analytical expression for the kernel, what do we see? It has 2 parameters, alpha and L. Alpha is amplitude. Actually, maybe you tell me. It's like, what does alpha do? What does L do? I know it's written there, but maybe you can describe in your own words. Yeah, what's alpha for?
Alpha increases the variance.
Great, yeah. So it's also, I also chose the notation alpha not to confuse with other sigmas. Often it will be written here as sigma squared, which would be marginal variance, right? What is L? What does L do? Yes?
The length scale, so it defines at which distance points influence each other.
Great. So length scale tells at what distances points are still strongly correlated with each other, which means if length scale is very long, we will be getting smooth, like long dependencies, right? So the trajectories will be smooth. And if length scale gets shorter, then we will be getting wigglier curves. So L is the wiggliness parameter. It defines how wiggly the functions are. Those parameters usually are not given. We have to infer them, whatever inference method we use. And here we can also start developing intuition for similarity. For example, if we fix alpha and L, then start varying, as a mind exercise, values of x and x prime. So the further is access to each, closer the axes to each other, then the expression is closer to 0. The further away they are from each other, we understand, okay, this function tells us about how similar are values at x prime. So that kernel is wonderful. We will work with it today again. But another class of kernels is the Matern class. Why is RBF kernel or squared exponential kernel is not enough? It leads to very smooth trajectories. And imagine data where their trajectories actually are very wiggly. So if we try, we still can use the previous kernel, but it will lead to incredibly short length scales and probably inadequate overall trajectories. So another way to fit models to such data is to use Matern kernels, which allow us to have rougher paths. And they're parameterized with parameter nu. If nu goes to infinity, then this kernel also turns into Matern, which is incredibly convenient. Here's a list of some kernels. So we say kernels correspond to function properties. This is a list of some cases we might want to pick from. For example, if all we want is continuity, we pick Matern 1/2. If we want to encode linear functions, we look up this table on the right. Okay, here's a linear kernel. If we want 2 times differential functions, here is Matern 5/2 kernel. There is a whole lot of incredible visualizations online, and the second in the list is from T again. I give you some options. You will have access to the slides. You can click on the links, go online. Some of them allow you to play with points. Some of them show you marginals. And of course, the most useful exercise after you went online and played with realizations online, most useful exercise is to go implement a particular kernel yourself and actually see for yourself what trajectories do they generate. All right, it turns out we can also combine kernels. If we have 2 kernels, K1, K2, there are ways to put them together to make new kernels. So if you know your function is linear but also periodic, you can multiply them. So we can multiply kernels, we can sum kernels, and we can create a whole library of new kernels from old kernels. Right, what we want to do though, we want to work with data. Usually we work in the setting where we don't have access to F directly. We might be able to get some noisy observations of F with some noise with variance sigma. And what we want is we want to predict the values of our Gaussian process at unobserved locations x star. We'll keep this notation throughout, and x star has n star entries. So n inputs, n star prediction locations. This is a very convenient way to summarize who is who. Again, that's not the notation we will use throughout. Everything without a star and big N, observed locations. Everything with a star, like x star, f star, k star. Okay, we'll get to k star. Everything with a star is observed. So what are the k's on the right? The first k is the gram matrix evaluated at observed locations. Second, k star is evaluation of kernel at unobserved locations, so at the prediction points. And k star, excuse me, is pairwise cross correlation, observed and unobserved, and K2 stars is unobserved only. So how do we make those predictions? And what we need to know here is two main properties of the multivariate Gaussian. Again, I should have asked you probably what they are, but here again on the slide, there are two properties. Is that if we have two multivariate normal Gaussians, x1, x2, we stack them together, two properties to know. First is that joint distribution is Gaussian, and conditional is also a Gaussian. And for this conditional, we explicitly know how to write a mean and covariance. How does it help us in Gaussian processes? Well, if we stack y and f star together, we also know how to explicitly write the mean and covariance function for the conditional. So if we want to predict what are the values of Gaussian process at unobserved locations, we know how to do it explicitly. There are some issues here. I'm sure also you would have discussed yesterday that this matrix pops up all the time. So there's K and some additions, and we want to invert this K, and that has cubic complexity, and it has quadratic space complexity. Space complexity does not bother us too much, but time complexity really is an issue. And bringing it back into MCMC world and probabilistic programming languages, we would not need to know how to make inference by hand. It was useful now to look at it to understand what the complexity of the problem is. However, when we're using probabilistic programming language, remember, we are just writing the simulation for the generation of data forward. So what we would write is, here's the observational model, here's where Gaussian process comes in, and there are some parameters in this whole story, and we need to give all of them priors. Then we press the inference button, and an MCMC algorithm will do the magic for us. So bringing it back home, all we need to know how to do is to formulate how to sample from a Gaussian process prior. However, having seen that statement about complexity, it makes the whole story a little bit scary. Okay, inverting the matrix one time has cubic complexity, and now we say we live in the MCMC world, which is an iterative algorithm, and if we want to run, whenever I said it has theoretical guarantees at infinity. So if we run it for infinitely long time, the conclusion is that it's really beneficial to run MCMCs for a long time, not infinite, but t is not a negligible number. So it's not 4, it's not 10. It's rather hundreds of thousands or maybe tens of thousands iteration. So this is what the complexity of our models where it leads us to. It's t times n cubed. Not great. Well, of course, it depends what t is, what n is, but in general, not great. And we need to be very clever about how do we sample from this priors, how we formulate those statements. Okay, let's summarize the kernel view. What have we learned? This is a moment representation, because we give definition via defining moments. We give the definition by choosing kernel. What's great about it is it's very incredibly intuitive, provides us distribution of functions, and choice of kernel corresponds to the choice of a function class. And the covariance function then encodes also the similarity between points. Right, next view is the weights view. And again, this is a view I bet you would have spoken about yesterday, or at least touched. And this view tells us that GPs can be viewed as a Bayesian linear regression, or rather, other way around. Bayesian linear regression can be seen as a special case of Gaussian processes. Here we fall into the world of curve fitting. I don't know about this year, but last year I remember Karl-Henrik started his talk about cycling, about fitting curves. So we now come into Karl-Henrik's land of curve fitting. What does it mean? We have pairs of observations, x, y, y, y. Somewhere we can plot them, and then all we want is to fit a curve. How can we do that? Well, let's say we assume the data has some noise sigma, but overall the trend is some function f theta of x. All we need to decide is what is the functional form of f, and what are the parameters theta, and how to estimate them. Okay, option one, it could be linear, right? We can say f theta, theta is actually two betas, beta 0, beta 1. And in reality, we can write it in much more concise form as beta transpose times phi, where phi is the so-called feature map, right? We can always say that phi is a vector which consists of two basis functions, 1 and x, and then the span of these two functions, 1 and x, give us all linear functions. So we are in the Bayesian world. Parameters beta 0, beta 1 are random, and we draw them from some priors. And what's interesting here, every time we draw from parameter beta 0, beta 1, we get two values. We plug them in, and we get a line. Then we draw a new pair, beta 0, beta 1, we get another line. So with this expression, beta transposed phi, we encoded many, many, many lines. And this way, we now obtain, so f theta now is a stochastic process which encodes priors of lines, of linear functions. And what does it mean to do Bayesian inference? It means to throw away those lines which do not describe the data well. Well, making any inference in the citation means taking all the possible lines and then adjusting for only keeping the values of parameters which correspond to the lines which are adequate with respect to the observed data. Well, if we took linear basis, nothing prevents us from using polynomial basis. Now, our basis functions from being 1 and x actually are all the degrees of x till m. However, in a concise form, we can write it down in exactly the same way, beta transposed phi, right? Beta is a vector of parameters, phi is a vector of features, the feature map. Previously, it has 2 entries. Now it has m plus 1 entries. I, of course, forgot to write phi not. But the meaning is the same. Every time we draw values of beta, we get a new function. So this way, by saying f equals beta transpose phi, we posed a prior. This is, again, a stochastic process, which is a prior over a polynomial of a wide range of nonlinear functions. So performing inference here, again, means throwing away lines which do not correspond to the data well. So what was not great with linear functions? Well, they were too restrictive, right? We see that our data fluctuates a lot, linear trends do not at all. Polynomial functions, so the result here looks already a little bit better. The problem is that they are very prone to overfitting, and then they explode in the areas, say at plus minus infinity, they will just explode. We don't have any data there, but they will give us very large values for no reason. That is not a good property. Another interesting basis is Fourier basis, trigonometric functions. They are bounded, right? So at infinity, they won't explode, but they have another caveat, and that they're not local. So they will fit the data quite okay here where we have data, but then if we add a data point here in the observed region, the function will be updated, but it would also be updated elsewhere, right? If it's a sinusoidal curve, it will get updated there at infinity where we have not collected any data. Not great. So turns out we could take this familiar basis, the squared exponential. They're just a set of bumps. So if we take any function, we can fit it very closely with a set of bumps, but what we need to decide is where to place the locations. And here, the effect is slightly opposite from the Fourier basis, that at infinity, it all gets squished. There's no uncertainty. As you can tell, we predict pretty much 0 at plus and minus infinity. Also not reasonable. Why would we do that? So what would happen if we took this basis, which sounds like a great idea, and just placed it everywhere? At every point, we would put such a bump. And remember, we are in this beta transposed phi situation. We know what the basis functions are, phi, great. Betas are the parameters, but then our problem becomes, if theta becomes infinite, then beta becomes infinite. And we are in a situation where I need to estimate infinite number of coefficients. Great idea, but a little bit problematic. So large phi here are matrices where we collect evaluations of feature maps, phi, and just stack them together. So we do not know how to work with problems with infinite number of parameters, but it turns out that all we need are actually pairwise products of phi at point xi and point xj. So it turns out we do not need to explicitly evaluate features. We rather can evaluate products directly, and that is the so-called kernel trick. This is an example. You can advise to go with pen and paper at home to make things clear. So what we know now is that we are able to place this wonderful bump at every single location. And that, as you might have guessed, corresponds exactly to Gaussian process with squared exponential kernel. So the next point of being sloppy, let's once define the scalar product in the space of sequences L2. And we will denote from now onwards this is phi transposed phi. So why am I being sloppy? If phi is a vector, completely okay to write phi transposed times phi, right? If phi is infinite, well, what is phi transposed? Being sloppy. But every time we write this, we understand this is the kernel trick. And I will not be mentioning the L2 scalar product again. So it turns out, any valid covariance kernel K can be written as the scalar product of some feature map phi at point x times feature map at point x prime. We do not need to explicitly compute, evaluate the features. And that also gives us a representation for Gaussian process jaws. So K is the kernel, and it is generated by a feature map phi. Then F, the Gaussian process, is generated by feature map phi as well with the coefficients beta. This is the linear regression, right? That's what we just saw. And the only difference from what we just saw is that the sum is infinite. So we took standard linear regression, generalized, generalized, generalized again. Things became infinite, but the overall form didn't change. And of course, this form gives ideas to many approximations. So we can always take this sum, infinite sum, and make it finite. And that gives ideas to how we can approximate Gaussian processes. So that was the second view, right? Regression view. Third view is the spectral view. What does that mean? So feature map phi gives rise to kernel. What's important to say is that feature phi is not unique. We might choose, there are different choices of phi we can make, which still will lead to exact same k. Well, a trivial example is, no, let's not talk of scaling. Feature phi is not unique. The question is, how do we choose these features? Sounds like an incredibly convenient representation. A related theorem is Mercer's theorem, which says if we introduce an integral operator, what does it mean? We know what a kernel is, right? K. Take some function psi, and just any function of x. Multiply k with psi and integrate it out. It gives us a new function of argument dot. We can plug there some x prime, right? So the result on the right-hand side is a function, which means we took a function psi and mapped it into another function. This is what this operator does. So if we find eigenfunction and eigenvalues of this operator, and this means L of psi equals lambda psi, turns out that the kernel can be written as an infinite sum of products, eigenvalues, lambdas, then eigenfunctions psi at inputs x and x prime. So thinking of operators is hard. As thinking of infinite GP is hard, we always say, oh, don't think about infinite objects. Think about finite multivariate Gaussians because we understand how to work with it. So equally, thinking of operators is hard. Let's think about matrices and vectors. So whenever we say function, let's just say, okay, function is always evaluated at points. If I choose a set of points from x1 to xn, evaluate it, I get a vector, right? So function corresponds to vector. When we say operator, again, think of operators as hard. We can think of operators as matrices. So to make it easy, this last line, we can think of just AV equals lambda V, where V is a vector, A is a matrix. And looking at the decomposition for kernel, we might start developing an intuition. So if K was not this function of two inputs, but a matrix, then we would be able to find such a decomposition, which will turn out to be useful later. So we can decompose K into product of a matrix U and diagonal matrix lambda in the middle and use orthogonal. Okay, so far it probably doesn't make too much sense, right? But where it does make sense, we said feature map phi knows how to generate K. K can be expressed via features phi, and then F can be expressed as basically linear regressions over phis. Now, Mercer's theorem gives us a bit of an instruction already how to find useful functions. It says, solve this eigenvalue problem, find function psi, and this is an instruction of how to construct kernel. And once we know how to construct kernel, we also know how to construct F. So Karinilova is an incredibly instructive way of generating Gaussian process prior. So it's linked to Mercer's theorem in the sense that psi's are exactly the same psi's here. They are eigenfunctions. Lambdas are the eigenvalues from the eigenvalue problem. And then, well, we do need some randomness in F. And where does it come from? We multiply every entry with Z, where Z is standard normal. Incredibly useful representation, as we will see not once, very soon. Okay, summary so far. Weights view means pick feature map phi. It will lead to a kernel. Mercer's theorem says don't take just any feature. Choose some very specific functions, psi, which are solutions of the eigenvalue problem. What is another view is, first let's recap the Fourier transform. Here I'm being unsloppy by defining Fourier transform. So Fourier transform takes a function of, on a real line, of course, can be generalized to RD. So let's talk about real line. We take function that maps real line to real line. How do we find Fourier transform of it? We multiply the function itself by exponent to the power minus 2piwx. X is the argument that function f depends on, but w now is this new term. And if we integrate x out, what's left is the function of w. Why am I being unsloppy? Because a lot of literature writes this without 2 pi. Should have put footnote. Unsloppy for once. Does everyone know what I is? Who doesn't know what I is? I was told by a friend before coming here, he's like, don't assume everyone knows in the UK about complex analysis. J. Okay, is this a cultural thing like tea and chai, depends where it came from in the world? Okay, I or J. So this is the imaginary unit, right? Does anyone here not know about I's or J's? Okay, fine. All we want to know about them is that if we square it, it equals to 1. If we put it to the power 0, it equals, squared minus 1. Power 0, 1, and the Euler formula that links exponent with complex exponent to sines, cosines. Okay, why is it important? If in practice I gave you a function f and told you here's f of x, go compute s of w. This is what you normally would do. You would plug f, then substitute the exponent using Euler formula, and go ahead integrating by parts. So inverse transform, we know how to transform from the original space x into the frequency space. So the omegas are frequency, and S of omega is the spectral density. What does it mean? Imagine if f was an actual trigonometric function. So if we found the spectral density, it would probably give us just a spike at the frequency at which function f oscillates. Okay, we can define also inverse transform. How do we go from the frequency space back into original space? Well, we multiply now by complex exponent, but with the plus sign, again, being unsloppy. I do keep the 2 pi here. So we know how to get from f to s of omega. We know how to go from s of omega to x. Stationary kernels, I guess you also would have defined yesterday, are those which depend only on the distance between 2 points. So they're called also translation invariant. So we can substitute arguments xx prime here just with one argument tau, where tau is the width of the sliding window. Okay, 2 important theorems, and I have collapsed them into one, because what's important is that we know how to go from f of x to s of omega into frequency space. We know how to go from frequency space back to kernels. So previously we were just working with abstract functions, but now we're talking about kernels, not just any f. So it turns out for every stationary covariance kernel, there is a spectral density. And the spectral density can define the covariance function. And that is, and I remember when we started by I asked you, how would you define a Gaussian process, right? How do you sample? And of course an answer was, multivariate normal Gaussian. Absolutely correct. It's not the only answer. Turns out we can define a spectral density. Yes. So this one, so Mercer's theorem was not explicitly linked to the dual space. This, so what I'm showing actually is Wiener-Khinchin theorem, because Bochner is somewhere just the half of it. So what we're looking at is Wiener-Khinchin theorem, which links the two dual spaces, the X space, where f of x lives, and the spectral space, where spectral density lives. That is the magic, saying that in order to say something about these Gaussian processes, we actually just can say something about its spectral density. Okay. Here are some examples. We can take the kernel, do that integration, and arrive to the spectral density. So what's, again, useful about that expression? Remember what we said about Euler's formula, sines and cosines. So if we stare at the expression for the Fourier transform, we notice that, well, S of omega is a density, and this expression is the expectation of the exponent with respect to this density. How useful is that? Because if we use Euler's formula and take the real part of both sides, we just get that kernel of a stationary process can be written down as, well, think of it as sums or, well, weighted sums of cosine functions. How incredibly simple is that? And we will come to this later. We will link back to this fact later. Just a couple of examples before we move on. For squared exponential kernel, this means that, well, we take the cosine and we multiply it here by the spectral density, which is an explicit function, right? We just now showed a table of explicit functions for spectral density. This is a simple function of argument omega. We plug it here, multiply with cosines, and here we get the kernel. That was the third view. Now the last view is the SPD view, stochastic partial differential equations. So it has been shown for particularly Matern kernels that Gaussian processes with these kernels can be viewed as solutions of stochastic partial differential equations of this form. So let us understand what this formula is saying. Okay, delta is the Laplace operator. I guess nothing wild about it. Differential Laplace operator. It means we take second derivative with respect to every variable, then sum them up. Nothing wild about it. Adding a constant to an operator is also nothing wild about it. But what does it mean to take a differential operator fractional number of times? How do we deal with that? So what this expression says, if you take a function f, somehow take fractional derivative of this function f, what you will get is a white noise with unit variance. Okay, so this expression is called pseudo-differential, not just differential operator, like nice Laplace, but pseudo-differential operator. How do we deal with it? What do we do? So how do we even take a fractional derivative? Okay, so we have function f. We take f prime. That's clear. How many derivatives have we taken? F prime. 1. F prime prime. 2 prime, right. So now we want to take f 1/2. Who knows what to do? Sorry, someone said something? What do we do? What do we do? What do we do? What do we do? So it turns out that if we apply Fourier transform to a derivative of a function, that looks incredibly simple. So first of all, let's agree the derivative f1 prime is wild, right? It's absolutely, does everyone understand what the problem? Someone does not understand the problem. How to take half derivative of a function. Wild. So what Fourier transform does, okay, remember we have function, now changing notation just for a little bit to talk about Fourier transform and derivatives. Some function y of x, nothing to do with Gaussian processes, okay? We take Fourier transform of it, gives us s of omega, some function of omega. So it turns out, if we take Fourier transform of y prime, all it gives us is the same function s of omega, it just multiplies it by I omega. And how do we get there? There's tiny bit caveat also about the functions that it's applied to, because to get to this expression, we need to integrate by part. So remember how to do this? We need to compute integration. So in R, it would be integrate from minus infinity to infinity, y of x, e to the power minus 2 pi iw dx. Okay, so f times exponent to some power. We integrate this by part, and that means there are some boundary conditions coming up there. That's why, written in small font here, we assume that we're dealing with good functions which vanish at infinity. But again, generally it turns out that taking a one derivative is equivalent to just multiplying the image, multiplying this s of omega by I omega or j omega if you come from that part of the world. What does it mean to take now two derivatives? Oh, sorry, Fourier transform of two derivatives. Well, it means take first derivative multiplied by I omega, means we're just multiplying the image by I omega to the power 2, which is minus omega squared. And we can continue it. So the whole, imagine we had a very complicated differential expression on the left. What we're getting on the right is s of omega times some polynomial. And the simplicity can help us solve differential equations because we're transforming differential expressions to algebraic. Here's a simple example. Ordinary differential equation. Y prime is presented here. Applying Fourier transform to left and right, what pops out here is I omega in front of the spectral density. Then we can express spectral density as some algebraic expression of omega. And to find y of x, we now just need to apply the reverse, inverse Fourier transform, bringing us back from frequency space to the original x space. Isn't it magical? So now let's take half derivative. What does it mean to take a half derivative of y? So we said taking a derivative, so taking a derivative of order k means taking s of omega, multiplying s of omega by I omega to the power k. That's it. So if we want to take derivative of 1/2, we take I omega to the power 1/2. And this is it. So here we had some function f of x. Applying Fourier transform on left and right, what comes on the left is s of omega. On the right, some simple function. To take now half derivative, multiply left and right by I of omega to the power 1/2. And we need to compute the inverse Fourier transform, which means taking integral, which I was too lazy to do, but this is definitely a function for which it works. Great. We understand now what this expression means. There was some differential operator to a certain fractional power. So what are the parameters I have not mentioned? We're talking about Matern kernels. So nu is the smoothness, L is the length scale, and then D is the dimension of the space in which we live, RD. So how do I understand this differential operator? In the Fourier terms. We can always send everything to the dual space, do some algebra there, and bring it back by the inverse Fourier transform. Okay, here's a summary of the 4 views. Kernel view, intuitive, very familiar. Moment representation defines price of functions and encodes similarity between points. Weights view make us think of linear regression. Gaussian process is just beta transposed phi, where phi happens to be infinite. Spectral view gives us instructions. It's quite informative of which functions are good. So solutions of the eigenvalue problem are good, phi's, the Mercer theorem, but also periodic functions are really good, in particular in conjunction with spectral density. And the last view is that we can think of GPs as solutions of stochastic partial differential equations. I've only written expressions down for Matern kernel, but the same holds for squared exponential as well. So that was your introduction 3 to Gaussian processes. What's left is actually some practicalities. What can we make out of all of that? And I need to say, of course, there's a million tricks. You can treat this third part as a bag of tricks. Of course, not all of the tricks in the world. I'd say they are the tricks which exist in a little bubble where I live in. So collaborators around me and myself, these are the tricks that we often use. If you ask someone else, ask Carl Henrik, ask Arthur, ask T, they probably use other tricks. So, some of those tricks they also use, but everyone in the pocket will have their own bag of tricks. So today I'm kind of turning my own pockets upside down to show you what's in there. And the first, kind of trivial but very important, is the nugget effect. So imagine we work with Gaussian processes, which we are evaluating only on 4 points. And so none of the points are identical, but 2 of them happen to be very close. And this just leads to some numerical unpleasantries. Imagine you work with, you can pick your favorite kernel and then hand by hand go write down expressions, and you will soon see that 2 rows. So imagine that numerically, points 2 and 3 are identical. You know they are not, but then the distance is so close that numerically to your machine they look very similar. So without you knowing that points are leading to a trouble, then your matrix K becomes degenerate. Very unpleasant. What to do, and tiny, trivial, but important trick is to add the so-called nugget effect, or often called jitter. It's really just a numerical procedure where you add tiny, tiny, tiny error to the diagonal. So once you add something very small to the diagonal, your matrix is suddenly not degenerate anymore. That's it. Nothing else to say about it, just one slide. Cholesky decomposition is the next trick, slightly more involved, more important. So we said that inversion of matrix K has cubic complexity, really unpleasant. Turns out also that this is a numerically unstable procedure. What is a more stable numerical procedure is finding the Cholesky decomposition of matrix K. What does it mean? So for any matrix, which is positive definite A, doesn't have to be linked to Gaussian processes, turns out we can find a lower triagonal matrix L such that L transposed equals A. We can think of L as the square of A. If I was even sloppier than I already am, I would just write L equals square of A. Okay, we usually write L equals Cholesky of A. This operation also has cubic complexity, so it does not solve the complexity issues, but it does solve a numerical stability issue. And we can think of Cholesky decomposition of matrix L here as analogy of the one-dimensional reparametrization trick. What does it mean? So in dimension 1, if we had a vector that was normally distributed with mean, mu, variance, sigma, we could always write it like this. The first parametrization is called central. This one is called non-central. So analogously, basically important is here, it's not sigma squared, right? It's on the linear scale, sigma times z, where z comes from the standard normal distribution. So analogously here, we can write f equals mean plus Lz, where L is the Cholesky factor. And we can compute, and due to the property of how Cholesky was actually generated, we know that this would mathematically be equal to matrix K. Computationally, the Cholesky would be more stable. Great. So the algorithm now for Cholesky is as follows. We still first need, of course, to sample parameters of the Gaussian process. Then we can evaluate matrix K. Remember, evaluation is not the same as inversion. Evaluation is not expensive. Then we can find the Cholesky decomposition, sample from the standard normal, which is very cheap, costs nothing, and then compute. So the answer, another answer, first answer, how do you sample from Gaussian process prior, was a sample from a normal distribution, perhaps with covariance matrix K. This is our second answer. I find Cholesky decomposition, and I multiply it by realizations of a standard normal vector. This is our second option. I already mentioned centered, non-centered parametrization. If we were thinking of a model of this form, where f was Gaussian process, of course we could sample simply like this. If there's little noise in the data, sigmas are small, then the data is informative, no problem, but much more convenient to work with non-centered parameterization. Okay, next trick is the Kronecker decomposition. Before I move on, in the bag of tricks, very easily one confuses where is the exact expression, where it's an actual equality, or where it is an approximation. So the Cholesky trick is exact, right? Is f equals Lz. We're not throwing anything away. We're not throwing any information away. No approximations. We're not cutting any sums. No, nothing. Kronecker is another exact expression. Very important. Because I heard some people, well, students that I work with, say Kronecker approximation. No, not an approximation. What is it linked to? To the Kronecker product. Again, just two generic matrices, A, B. What does it mean to find Kronecker product of them if first matrix is dimensionality Mn, the second was dimensionality PQ? The Kronecker product will be the big matrix, dimensionality M, P, and Q. I call it also each with each product. So this product will contain elements which are which have somewhere in it products of every element from A and every element from B. In terms of properties, very important, there's no inversion of order. Remember, if we take product AB to a power -1, we need to reverse the order. Here, not. Neither for transpose nor for a power -1. Introducing also the so-called VEC operator. Again, extremely simple. We just take the matrix. What does it mean to apply operator vector? It take all the columns and stack them one under another. So it's literally just mechanical reshuffling, reshaping of the entries of the matrix. And incredibly, the key property of the Kronecker product is that for any three matrices with proper dimensionality, the following holds. So who's who? A and B is a matrix, C is a matrix, vec of C is a vector, right? So what we're saying, this is a big matrix, this is a vector. So to multiply this big matrix by this very long vector, what I can do, I can find a vector which is stacking of the columns of this matrix. This will all make sense in a minute, because we want to talk about separable kernels. What does it mean, separable? It means that we can represent the whole kernel as a product of simpler components. And usually, if we are lucky, those components correspond to different dimensions. So if we're in R2, then this will be first kernel on the first dimensionality, and on x's, say, and the second kernel would work on y's. So imagine we work on this multivariate grid. Coming back to applied problems, so imagine we have the space, we have some observed points, and we create a computational grid. We just subdivide the whole space into pixels along x and y axes. And what is a great separable kernel? Squared exponential. Turns out squared exponential lends it perfectly to the Kronecker trick. Why? Because it has exponent of a sum of squares. So we can say this is a product of first kernel, which only works on x's, and second kernel, which only works on y's. Then the Cholesky decomposition, our trick we've just learned, we can apply separately to matrix, to covariance along the x-axis, separately to covariance along the y-axis. And, okay, we're not going to compute what's written in this line, but this is for us to understand. It turns out that if we wanted to find Cholesky factor of the full matrix K, right, then we would just Kronecker multiply Cholesky decompositions. I see many of you writing down with pen and paper, which is great, but this slide also will be available to you. So the key Kronecker property now, how does it help us? Okay, we want to compute this Gaussian realization Gaussian process F, which is very long. Now think of something, F now would be, if we have 100 points along x-axis, 200 along the y-axis, there will be 100 times 200 to the power squared, really many. So F is a very long vector. In theory, if we wanted to use Cholesky trick, we would need to compute this L. But we know that L now decomposes into the Kronecker product of two smaller L's. And if we apply the Kronecker key property, all we need to compute is small matrix Lx, small matrix Ly, and here Z is nothing else, just a standard normal, which is super cheap, costs nothing to compute, reshuffled. Okay? So Z is a matrix where all entries are still independent, so it's a very cheap matrix. And then this whole expression consists of cheap, small matrices. And then the final operation we need to do, we have computed this matrix. We just need to apply vector. Sorry, this is this is the vector operator. So take this matrix and then stack the columns together, and this gives us the long vector F. Okay, so no approximations were done here. What is this is the overview of the whole algorithm. What is the complexity? So the complexity mainly hides in finding Cholesky of small vector, of small matrix Kx, and small matrix Y. So we came from m times n to the power 3, complexity to, let's say, m is larger than n, to the just complexity of m cubed. Carl Henrik is looking at me, I'm looking at the watch. I'll be a little bit fast now, but I want us to get flavor of a couple more items here. So what we learned, Kronecker trick is exact, no approximations there. Complexity reduced incredibly well. Next trick in the bag is random Fourier features. So remember spectral representation, we said stationary kernel can be written as an expectation of cosines with respect to some density. And if we tweak around those trigonometric operations, really there is no rocket science here at the bottom of the slide. It's literally just adding, multiplying, cosines, sines. I had to look up those formulas because I forgot them since school. But it turns out we can rewrite the whole expression. So what we have on the left is k of this difference, but what we want is always 5x times 5x prime, right? We want x and x prime somehow separate. So we can do it just by rewriting in this way. Sorry, this is a typo. This is not y, this is x prime. And how can we evaluate this expectation? Well, expectation is an integral, right? Two ways. A, quadrature. Good but boring. Or using the magical Monte Carlo method. So what can we do? We can sample from proportional to the density and just form the sum, and this will give us the kernel. And this all comes down to features which are cosine, like sines, cosines. And there's nothing probably simpler, nicer than sine, cosine features. So that gives us an instruction of, I think, the fourth instruction, right? First, sample from multivariate normal with matrix K. Second, compute f of L times Z, the Cholesky trick. Third, the Kronecker product. Now, fourth, random Fourier features. And this is an approximation. So first time we're talking about something that's not exact is an approximation. A similar, related to this business, kind of linking Fourier view and SPD view, is the Hilbert space approximate Gaussian processes. So I won't talk too much about it, but you might recognize here integral operators and Mercer theorem. What is important, though, is that it gives us again an instruction of how to find eigenvalues lambda, how to find functions phi. They are solutions to the some eigenvalue problem. S is a known function, just as spectral density. So again, Hilbert space, HSGP for short, is another approximation. So first approximation, we saw random Fourier features. Second, we didn't see in detail, but you will have the slides and all the references are in here about Hilbert space. Especially if we are in some nice domain, we can solve everything analytically and get, again, analytical expressions both for lambdas and for functions. What I would like to skip through quickly and just talk a couple more minutes about graphs. Remember at the very start we said there's 3 types of spatial data. And what about graphs though? Okay, so it was a trick question because I started by talking about aerial data. And aerial data is described how? We say, here's adjacency matrix. All we say about each area is who is it neighbor with. Turns out that aerial data, even though it looks visually very different, is represented exactly the same way as graphs. So by talking about aerial data, I kind of already spoke about graphs. The problem with aerial data and spatial statistics is that the ways of model it are incredibly simplistic, very imperfect, and are not advisable. So we might borrow some wisdom from graphs. How do we work with graphs? Weighted graphs. Well, we describe graphs as a set of vertices and weighted edges, and we would like to define GP kernels on them somehow, and for example, matern. So squared exponential kernel, how can we apply it to a graph? We probably want to take some, remember we have 4 views on Gaussian processes. To define GPs on graphs, we probably want to generalize one of them. And now we just need to filter out and understand which generalization is great. So it turns out that kernel generalization is not great. Because if we plug in here some random distances, generically it will not lead to a well-defined covariance kernel. So it needs another generalization. SPD seems to be a good one, apart from this differential operator needs to be redefined, because that operator is defined in RD. What do we do on a graph? So for graphs, we again introduce adjacency matrices, who is neighbor with who. This is a matrix of either weights or just binary numbers, 0, 1. And matrix D is exact. So this expression we saw in the introduction. I just didn't call it graph Laplacian because spatial statisticians never talk to people who work with graphs. However, it's exact same matrix, A minus D. It's called graph Laplacian, and it will serve now as an analogous Laplacian to the differential one. So the differential one is minus delta to make it positive definite. Here it's a matrix, A minus D, also positive definite. And what is to say about it? That it can be decomposed same as we already saw for positive definite matrices. We can introduce functional calculus with respect to diagonal matrix lambda. So if we take any function g, what does it mean to apply it to lambda? It means lambda is a matrix, right? And G works on reals. It means we apply it element-wise to every element on the diagonal and multiply on left and right by orthogonal U. Okay, so what you want to hear probably is that the generalization we're looking for comes from SPDs. Remember, this has very similar form to the SPD where we discussed how on earth do we decide, how do we define derivative 1/2. This is, again, a similar expression. So we generalize SPD view to graphs. However, in the graph space, everything becomes simpler because everything becomes a matrix. Because the graph space is just vertices, right? And everything is defined by matrices. So we can derive analogous expressions as we had in the SPD view. And the answer is that through that SPD generalization, we are able to write down explicitly how a graph matern looks, or how, well, graph diffusion is the same as graph SE process. And it also allows for graph Fourier feature representation. And that is all. Of course, whatever I said is based on a bunch of references which you all will be able to find here. Also links for you to what I know was a lot of material, where to go from here. Of course, play around with visualizations. Also, to get intuition about MCMCs, there's another interactive gallery. Geometric kernels, the GPs on graphs. There are also notebooks which creatives of the library has created for you. If you would like to learn NumPyro, the last link is the whole course that teaches you how to go from 0 to hero. Very big thank you to organizers, second year in a row, to my other GP collaborators, and many thanks to you all for sticking around. That's all.